Hi everyone, welcome back to the basics of rheology. So far we've covered viscosity, viscoelasticity, how rheometers work, and even how to approach unknown materials. In our last episode, we identified the linear viscoelastic region, or LVR, using a strain amplitude sweep. That's a crucial step because now we can confidently run more oscillatory tests like frequency sweeps, time sweeps, and temperature ramps, all while staying within the LVR. But here's something important to remember. The LVR isn't fixed. It's sensitive to both frequency and temperature. At lower temperatures or higher frequencies, materials tend to stiffen, and that means the LVR narrows. So before you run your tests, make sure they still fall within the LVR under your specific conditions. Let's start with the frequency sweep. This test tells us how a material responds to different timescales of deformation. We apply a small oscillatory strain within the LVR and vary the frequency. Here's a simple way to visualize it. When I oscillate this shampoo bottle quickly, it is like high-frequency deformation. You only see some elastic wiggle. There is no visible flow. But when I slow down the oscillation, the shampoo starts to flow. That's exactly what a frequency sweep test reveals. In a frequency sweep, we measure storage modulus, the elastic part, loss modulus, the viscous part, and tan delta, the ratio of loss modulus to storage modulus. If tan delta is below 1, the material is more elastic, like a spring. If tan delta is above 1, it's more viscous, like syrup. And if it's exactly 1, that's not just a coincidence, it's a transition point. It often means the material is shifting from solid-like to liquid-like behavior, or vice versa, a moment of balance, and a key insight for rheologists. Some examples for applications of frequency sweeps are estimating polymer molecular weight and distribution, and scouting difference between formulations. Next up, the time sweep. Here we apply a constant oscillatory strain at a fixed frequency and just watch. We monitor how the material's moduli evolve over time. This is perfect for studying curing, like gels or resin setting, recovery after shear, and stability. Does the structure hold up? Let's say we are testing a gel that cures over a few minutes. In a time sweep, we'd see the storage modulus increase as the structure forms. If the storage modulus crosses the loss modulus, that's a sign the material has transitioned from liquid-like to solid-like. Or maybe we shear a cream and want to see if it recovers. If a storage modulus bounces back, great. If not, the cream may have undergone irreversible structural damage. Time sweeps are like rheological time-lapse photography. You set the stage and let the drama unfold. Finally, let's talk about the temperature ramp. Here, we apply a constant oscillatory strain at a fixed frequency and gradually change the temperature. This helps us study thermal transitions like glass transition temperature and stability. Does the structure hold up as it heats? Think of something like a gelatin dessert or wax. At lower temperatures, it's firm, storage modulus is high, and the material behaves like a solid. But as we heat it up, the structure starts to soften, storage modulus drops, loss modulus may rise, and the material becomes more fluid-like. Temperature sweeps are like turning up the heat and watching the material reveal its limits. So to summarize, frequency sweeps show how materials respond at different time scales. Time sweeps reveal how materials change over time, and temperature ramps uncover thermal transitions and stability. Each test gives us a different lens into the material's behavior, and together they help us build a complete picture. In the next episode, we'll shift gears and explore transient tests like creep and stress relaxation, and how we can use them to analyze viscoelasticity. Thanks for watching, and keep wiggling those samples.